This is a solution to the linear angular problem. The car moving on a road where we're looking for the number of revolutions of the tires. So normally what happens in these things is you're usually looking for the opposite of what you're all given. In other words, if you're given all linear terms, you want something angular. If you're given all angular terms, you want something linear. So understanding units is really, really, really key. So as you read the question, you are given a bunch of linear terms. And I usually set them up like this. Put a little L for linear. And on the linear side, I usually draw a picture just to make sure. So what did I have? I had a start and an end. I'll even draw an axis. But you were given at the start a car 12.2 meters per second. Well, let's just make a list of what we know, like we normally would do. V0, 12.2 meters per second. You were told the acceleration, 1.97 meters per second squared. And you were told the time, 5.22 seconds. So this is all given information. And then the question said, through how many revolutions did one of the tires make? That's angular. So what I'm going to do, even though I may not have any other equations here, is just write down what I'm looking for under angular. Kind of keep it all lined up. I want delta theta in revs, because that's the number of revolutions of a tire. So what you can try to do now is one of two things. The long way would be to convert every linear term to its angular counterpart using the link equations. That just takes longer. Or, if possible, try to figure out the relationship between what you're looking for on the angular side and what you want on the linear side. So, angular, you want delta theta. The linear counterpart is s or delta x. So when we have the link, we can use this. S equals r delta theta, where you're thinking, again, s is really delta x. Now, why will that help you? Because then delta theta will be delta x, which is s, divided by r. So all we have to do is get delta x and r. Well, let's get the radius first. Easy enough to do because we were given the diameter. So I'll kind of just put that down here somewhere. The radius, half the diameter. So that would be 12.35 inches. You got to be very careful. Sometimes you're given a diameter, sometimes you're given a radius. Well, we got to get it to meters. Times 0.0254 meters per inch. And that will then give you 0.314 meters. So there's the radius. So all we need is delta x. Let's go back over here and get delta x. And the other things we don't need v or v bar. But now we can get delta x by this equation. Delta x, v0t plus 1/2 at squared. We've got all those numbers and we can put them in. And if you do, you would end up with 90.5 meters. So there's delta x. So that's how far the car actually went. Now we can find delta theta. 90.5 meters over the radius we just found, 0.314 meters. Now look, you will get radians out of this equation. You have to. Meters divided by meters. That's radians. Remember, radians is a unit that is really an arc length divided by the radius, so they both are units of meters. So when units cancel out and you have absolutely nothing, it's radian based. So this is radians, and what it is 288. And now we have to 1 rev, 2 pi radians, and we end up with 45.8 revolutions. And that's the answer. And our quick check, it's less than 288 by roughly a factor of 6, so it's probably good. So this is just one type of example of a linear to angular. They're all very similar. You're going to have a linear, you're going to have an angular, and you're going to have a link. So the easiest thing to do is try to solve everything in one side, either the linear or angular, use one link equation, and you should be able to be successful at solving these problems.